Okay, looks like we can start. Welcome back, folks, and congratulations on getting through the third exam. We have not too many weeks left in the semester, and we'll be doing our final exam on week 16, finals week. With what we have going on today, we're going to be moving through section 8.1, law of sines, and getting started on section 8.2, law of cosines. And pretty much this is what our goal is for the week, also working on the polar coordinate section 8.3. But I don't have too many announcements beyond that, other than just like on your other exams that were returned, your course grade on exam 3 is just your current score to date as of Saturday morning when I finished grading the exams. If you don't have your exam back, check your ISU email. If you still don't see it there, just send me a message either through email or Canvas, and I'll get your exam sent to you right away. But any questions at all, folks, before we get started with today's work? Okay, well, these are some pretty exciting sections, law of sines, law of cosines, and even polar coordinates, even though this section is more of an application that we're going to see, you would see again in a Calculus 3 setting more likely. Still, it's a pretty interesting topic in its own right. For what we've got going on with the upcoming week is after week 13, we'll take an entire week off. This is going to be kind of a catch-up week for me. When I'm on this week, probably Monday and Tuesday, what I'm going to be doing is filling out the information, the details, the review problems for finals week, getting everything all set up. And also just as a reminder for this course, if you've got behind on a few sections, it happens to the best of us. I take problem or section homework sections at full credit, even if you turn them in late. So this could be a catch-up week for several of us. If you're getting caught up, if you have questions, don't hesitate to reach out by email. I'll still be available. I won't be checking my email necessarily the entire time during Thanksgiving break, but I always check my email just at the start of the day, at least as a habit. Well, let's jump in then, folks, to section 8.1, law of sines. Where we left off was right here on finishing off this problem right here, example 3. And I think I recalled making an error during the last 2 minutes of class. So thanks goes out once again for David for catching that. Just as a kind of a warm-up and how law of sines goes, first, here's the full statement of law of sines. It's overwhelming because there's 3 equations here, 3 more equations here, really. A triple-sided equation really implies 3 equations you're looking at. But it's really all about the relationships. The first line here is just a reciprocal of the bottom line. What this is saying, essentially, law of sines is we look at just one equation at a time. In solving this triangle, we need to find the unknown side B, the unknown angle A. We just used the idea that the interior angles of that triangle had to add up to 180 degrees. So subtract 110, 32, and that gave us the angle A right away. Last thing to do was to solve for side B. So we used this bottom row here for solving for sides. Sometimes it's the convenient set of equations because the unknowns are up in the numerator. So we took B, the side, divide by sine of the side B, then took A, divide by side, the sine of the side of A, 38 degrees. Plugging in that information, we can solve for B immediately just by doing this halfway cross product, clearing the denominator. And that got us the last part of the problem. Oh, looks like we used law of sines here as well. So 2 applications of law of sines, and just the principle got us that angle. We'll practice this a couple more times before we move to the next section. But any questions, folks, looking at the warm-up problem? Okay, so this triangle was solvable. We could find all the interior angles, all the side lengths. The next problem is kind of weird, and there's one like this in the homework. It says, show that there is no such triangle, that this is impossible, that it would have a side length A is 2, B is 6 in feet, and an angle measurement alpha is 23.1 degrees. And maybe some triangle like this might exist, but not with the way we write down our triangles, with side A and angle A being 23.1 degrees. That actually makes this really restrictive. So let's write out about what this would look like. Here is a side length of 2 feet. Already this might seem kind of weird. We're told there's no such triangle satisfying this, And yet here we go, we're writing down a triangle. That's just so we can organize together all the information and see how law of sine is applied. And then we'll see, even though we drew it on paper, this is not something that would exist on a plane. So there's side length A, side length B is at 6 feet. So I'll just try to make it look proportional. Here's B equals 6 feet. Here's another side length, here's C. And these two sides have to tie together in this way. If we have a side length A, then the angle, whether we call it alpha or uppercase A, has to be on the opposite side. So alpha must be here. This is what's making it impossible, that we could just drop alpha anywhere we wanted. It has to be specifically to the opposite of the 2 side feet and have this side length of 6 feet here. Or we could have drawn 6 feet here and it's still been an impossible situation. So this is the 23.1 degrees. Just so we can fill out the triangle, let's add some more angles. Here's angle gamma, opposite of C. Opposite side B over here in this corner would be the angle beta. And if you just decide to use uppercase A, B, C, that would have been just fine as well. So after tying those two pieces in, we'll use law of sines. Well, we're told there's no such triangle satisfying this information, and we could solve for possibly a side length C, except angle gamma is unknown. So if we started to try to use law of sines in this way, C over sine gamma equals, maybe it's A divided by sine alpha. This is a big problem for us because this side right here has 2 unknowns with 1 equation. So this tells us law of sines can't be used in this situation. We have to have 3 known values and just 1 single unknown. So let's just write that out as a comment. It's good to know when law of sines can't even be used. And this would be one situation. We cannot use law of sines unless there is exactly 1 unknown in our equation. And here's the problem. Both C and alpha, so sine alpha as well, are unknowns. So we can't start the problem out just like we did on example 3 at all. We have to focus instead on the angles. We can do potentially something with the angles. This is an unknown beta here, but we have a known side length B, a known angle, another known side length A. So that would be just 1 unknown if we used beta here. So let's go that route. Here's an unknown beta with a corresponding side length 6 feet. So let's say sine beta. I'm putting sine of the angle in the numerator this time, since beta is the unknown. Divide by 6 feet, and I'll just write it in as a 6, dropping the units, equals sine gamma, or excuse me, that's an alpha, we're a little rusty on my Greek. Sine alpha divided by A. Might as well just reuse that color coding to remind where everything is in the triangle. So after plugging this information, we can say, actually, let me back off just 1 step here and call this B. And then just plug in all 3 values at once, so it doesn't seem like we're doing half the problem on one line and then the next. So this is the law of sines where it can be used, just 1 unknown right on beta. Plugging in the information, we have sine beta over 6 equals sine 23.1 degrees divided by 2 feet. And from this, we can solve this equation for sine beta. So sine beta is now equal to six sine 23.1 degrees divided by 2. So let's keep on simplifying this. Sine beta is 3 times sine 23.1 degrees. All I did on this line is divide by 2. And now this is the step at which we would just throw this into the calculator. 23.1 degrees is not a friendly angle to calculate at all. And so let me pull up the Desmos calculator. We'll use that. And just to practice this one more time as a warm-up, this is a calculator you might be using for this kind of work. You might have a slightly different kind of scientific calculator, but the idea will be about the same. Make sure it says degree mode because we're dealing with the angle and degree measurement. Over here, let me double check. Okay, we're in degrees as well on this one. And then all you'd be putting in your calculator is just, it's kind of tricky with multiple windows. 3, I need to change this tool here. There we go, so 3 times sine 23.1 degrees. And this is what your calculator would look like. Again, the thing to watch out for is you're actually in degree mode. So hit the degree button or the corresponding button in your version of the calculator to swap that up, make sure it's not in radians. And keep the idea handy because you might need to swap back to radians later on, just depending on given information. So that's what it would look like in a standard calculator. For the classroom demonstration calculator Desmos, looks about the same. 3 sine 23.1 degrees comes out as a 1.1770. So sine beta, 1.1770, and I should check my numbers on that. Okay, so we've got it there. Now we can solve for that angle beta by just taking sine inverse of both sides. Essentially, we're now just redoing the equation solving problems that we did in section 7.5, primarily the calculator version. But this might look kind of funny to you. Anyone see something that's kind of off about this equation or any questions at the moment in general? While we're thinking about that, let me plug in a quick graph on sine. And my sine graph looks really bad, but you have to remind yourself every time you're switching the mode, you have to switch back. A graph for a sine function automatically assumes you're in radian modes. So that's a graph I was expecting to see there. And this is what makes this equation really kind of odd. Thinking back on equation solving, as well as thinking back on inverse functions and graphs of the trigonometric equations, you'll only have a solution to this if the sine wave intersects the line y equals 1.770. And if you change the amplitude, it certainly will. There's going to be loads of solutions now. But we have ordinary sine, and so the amplitude here is 1. It never reaches 1.770. And if you weren't thinking along those lines, the graph, you might say, well, take sine inverse of both sides, like in section 7.5, but then you just run into this other problem. Arc sine 1.1770 is undefined. We had a question like that on the exam as well, I think for a cosine inverse, where something comes out as undefined as well. That's just because the domain of arc sine is between -1 to +1. You can never actually solve this value. So that's where this starts to come together. We have no solution right here because the value is larger than 1. No solution. And this tells us the triangle does not exist in the plane. So on flat paper, we cannot build a triangle like this whatsoever. Looks like we could until the moment we start looking into the details, and then something drawn on paper is not perfectly to scale. This turns out to be a lie. Well, any last questions, folks, on getting through this one? So I want to connect them.
Oh, go ahead.
Sorry, go ahead, Andrew.
Why did you flip the sign in the sorry, when you moved on, you flipped where sign B and B was instead of having it on top.
Oh, you mean from the orange line to this blue line here?
Yeah, I understand why we couldn't use sine C and I don't remember what that symbol is, but could have used
Yeah.
beta and B. I just don't understand whether you have B and A on the bottom on the denominator.
Oh, gotcha. The major reason for that was I decided to flip to the top row of these three equations for law sines only because I was trying to solve for the beta angle. So I went for the version with beta in the numerator. But we could have done it with this version as well, beta in the denominator, and the algebra would have came out slightly similarly, but very identical. It would have been 6 for this b in the numerator over sine beta. Let's call this just an alternate approach. And then if we flip this side, we would have had 2 over sine 23.1 degrees. But really, we're getting the same exact result because if this is our version right here, if we flip them both, like you said, the first thing we would do is clear denominators. But now it's a full-on cross product. You would say, take sine 23.1 degrees times 6. Let me keep that same color to connect the thought. 6 sine 23.1 degrees. Then it would be 2 sine beta on the right-hand side. And that would be essentially this step right here, right before we divide both sides by 2. So then our steps would match right at that line. So I guess the short answer is I flipped it with sine beta in the numerator only because that was the major angle I was solving for. And it made the algebra just like this much faster to get sine beta all alone.
Okay, but both would have worked.
Yeah, absolutely. That's a cool thing about law of sines. If you stick with angles on top on every problem or side lengths on top on every problem, it's always going to work out. Absolutely. Well, thanks for asking about that. Other questions at the moment? Okay, again, kind of a weird problem. It's interesting to know that you can write down these problems that make no sense whatsoever. You can trick yourself by writing it down on paper, but mathematically, you'll spot a problem immediately once you go to try to solve that problem. And for the next interesting problem, this one is kind of a fun problem. This is a problem that's a subtopic in, say, surveying, trying to find distances, angles, and those kinds of things. And this is a specific kind of surveying problem where we have two known angles. We have kind of using an intersection method where this line here and this line here intersects with something we want to find a distance to. It turns out using law of sines in this situation, maybe law of cosines in a different situation, is a great way to solve this kind of problem. So here's the quick graph on what's going on. It says to determine how far a boat is from a shore, 2 radar stations 500 feet apart find the angles out to the boat, as shown in figure 28. So here's our 2 radar stations. With the right tool, you can carefully measure these angles. And they already know because they built these with the intention of doing this kind of work likely. Distance from here to here, really this angle, this edge to this edge, is 500 feet. So here's the 500 feet. We want to determine the distance from the boat to the shore. So that'd be a perpendicular line coming down, heading here. And it turns out we can find this distance in a pretty fast way. We'll use law of cosines and then Pythagorean's theorem to make it happen. So here's the statement of the problem. It's kind of funny the way it's drawn. So this point A is really supposed to be here, and the graph is just conveying that information. But it's kind of visually noisy when you see all this, a drawing of a boat, radar stations. So one good strategy is you can just abstract away from the fact that this is a actual physical problem if you wanted to, and just draw your angle, your triangle rather. So here's the problem without all the noise inside of it. Here's A, B, C is the angle where the boat is. Using ideas from before, we can measure the angle C because if this is 70 degrees and this is 60 degrees, that's 130 degrees so far. We have to put down an angle here that'll get us to 150 degrees, 180 degrees, and 50 degrees is what would do the job. These three added together would give us 180 degrees. So that's pretty much how we started off our example 3. And if we dropped down that perpendicular, because we're trying to find the distance from the boat to the shore, here's what it would look like. Let me add the other information. We know that this is 500 feet. This would be lowercase c. Here's lowercase a, lowercase b. And we want that distance. There's a right triangle inside here. And, well, this gets us started. To get this distance, we could find the side length A, maybe the side length B, or vice versa. But it turns out we don't need both. We just need to pick a direction to go. Because the moment you have one of these two side lengths, you now have a right triangle you're dealing with, and you can just use ordinary Pythagorean's theorem to find this height right here, which is going to be the distance we want to find. Let's use a better color because this seems like an important part of the problem, find the actual distance. So we'll call this D. David says, isn't lowercase a and lowercase b supposed to be on the opposite side of the uppercase ones? Yeah, absolutely. Thanks for spotting that. That was a weird mistake I made on there. I mean, we possibly could solve it like this, but for using law of sines in this format, that's going to cause a lot of weird noise in our head. So thanks for spotting that one again, David. Lowercase a should be opposite of the angle A, like you said, and lowercase b should be opposite of the angle B. That's going to make this problem a lot more easier to put together. Other questions at the moment? Okay, well, let's apply law of sines and get one or the other. Well, let's go for maybe, I think they're both good angles. Let's go for maybe B on this one. If you like, you could take a different approach. I said angle B. Let's solve for side length B. If you want, you could take a different approach and solve for side length A. You'll get the same answer on this one. So if I'm going this route, I'm using the 60-degree measurement, and we can say that because I'm solving for B this time, I'm going to keep B in the numerator. B divided by sine uppercase B is going to be, here's the other side, A divided by sine uppercase A. So we take the opposite side, divide by sine of the angle over here on this end, and same thing with B. And double checking, we have to have, let's see here. Well, that's not going to work, right? Double checking, we have to have exactly one unknown in this problem, and that's two unknowns, A and B. That's okay, we can reverse this around. Let's leave this on the notes to say this approach fails. Since both A, B are unknowns. But you know what is known on this triangle is angle C. We've got that information, and side length C. So let's make this our second attempt on law and sines. So next go, take B over sine B, sine uppercase B. It's going to be equal to, let's take C, the known quantity, 500 feet, over sine uppercase C. And we can solve that one. There's exactly one unknown, B, in this setup. So this becomes B divided by sine of this opposite angle, 60 degrees. We know that exactly, but we're putting this all into a calculator, so we'll just not worry too much that this is square root 3 over 2. I think it's just simple as enough right in that form. C here is 500 feet. We can fill in. Divide by sine of 50 degrees. So from there, we can now solve for the side length B in essentially one step. Multiply both sides by sine 60 degrees. It just parks it right over here by 500 feet. So B is now equal to sine 60 degrees times 500 feet divide by sine of 50 degrees. And let me see if I can just fit in a bit more space on that. Last step is going to give us the length of B. So all that information shoved back into the calculator gives us sine 60. Remember, I swapped this to radian modes in order to do a graph. So let's make sure we're back in degrees. Sine 60 times 500 divide by sine 50 degrees gives us a side length of 565, I'll round to 2 decimal places, 0.26 in feet. And looking at the lengths here, it looks like it's somewhat commensurate with this being 500 feet apart. There's no guarantee that this triangle is drawn to scale whatsoever, but that does give us some assurance that we're on the right track. So this becomes 565.26 feet. So that was a lot of work. Thanks to that false start, makes it look like a lot more than it was. But we have a side length right here. So now we can take just this left side to the left of the blue dashed line, take this whole right triangle here, and solve for this side length D. That's going to be the distance from the boat to the shore, the main thing we want to find. So let's draw a new triangle because this one's getting a little bit full and messy. So move away from that one to the right triangle. We have 70 degrees going this way. Notice what information we lost though. This was 500 feet from A all the way to B. And I don't know exactly where this intersection is. It's not exactly halfway. You can see from this diagram as well. It's somewhere here, slightly less than 500, half of 500 feet. So this is really an unknown. This is something that you would have to solve for to come up with. But that's okay because when we solved for B, we got the hypotenuse. So the hypotenuse here, B, equals 565.26 feet, is going to allow us to solve for this height, D, which is the underlying value that we want to solve for, the distance from the boat to the shore. So once we solve for D, our work is done. Let's scroll down to make sure we have some space here. So all I've done is just extracted this section right here, half the triangle, well, not exactly half, but this left side, wrote in the right triangle, and now we'll use SOHCAHTOA, back to right angle trigonometry, to find the length D. Well, any questions to this step so far, folks? Okay, the SOHCAHTOA acronym tells us, well, we have just really 2 angles you could work with, really. This is 20 degrees right here. I'll just work based off the 70 degrees we see. Sine is the opposite side divided by the hypotenuse. The hypotenuse we have, that's the side B in blue. The opposite side, let me fix my color coding here real fast. The opposite side in SOHCAHTOA is the distance D that we're trying to solve for. So that suggests if we just take this part, sine of 70 degrees, it's going to be the opposite, D, the unknown, divide by the hypotenuse, B, which is 565.26. And from this equation now, just using good old right triangle trigonometry, we can clear the denominator doing this halfway cross product, and we pretty much have an answer. The distance D is 565.26 multiplied by sine of 70 degrees. So back into the calculator, we're going to round this one to, it says, the nearest whole foot. That seems kind of aggressive rounding, but let's go with it. In the calculator, this all boils down to 565.26 sine of 70. So it comes out at 531, rounding to the nearest whole foot, feet. Equals the distance from the boat to the shore. And so that's the idea with this kind of triangulation technique. If we have two known angles and a solid distance between the two spots where we made those measurements, we can find the distance from any point out there in this kind of way. And it's a pretty cool technique because if you want to map something out, if this terrain is completely inaccessible, in extreme case, imagine it's, say, something molten and you just want to map out an island inside of some molten lava, you can map that out just using this technique over and over again, finding distances between various points on that area that you are inaccessibly able to walk into. But it's kind of a big approach. We used law of sines, finding one angle, extracted the triangle, and then used the ordinary right triangle trigonometry to get the final distance. But any last questions or comments, folks, on finalizing this one? Okay, well, we did it, folks. This is law of sines in a nutshell. The cool thing about law of sines is really it's just based off an area formula. And the idea was if you use the area formula three different ways, you can translate that area formula into this relationship law of sines. But there's a pretty cool remark about class, a really great observation about this area formula, is that it's just an extension of this formula that we wrote down here. Area of a triangle is 1/2 base times the height. In the special case that it's a right triangle, area equals 1/2 base times the height sine 90 degrees is a pretty true statement because sine 90 degrees comes out as just a 1. So in a real sense, you pretty much are using this kind of problem as just an extension from the right triangle trigonometry. And carrying that analogy forward, when we go to law of cosines, it's the same kind of idea. Law of cosines is extending Pythagorean's theorem in the case that it's no longer a right triangle that you're dealing with. So just as a warm-up, let's draw a right triangle and then see what law of cosines is all about. 3 different equations this time. At least it's just 3. It's not a triple-sided equation. But first, here's our right triangle trigonometry. Here's the right triangle here. And often we'll call this leg A, so angle A over here. This leg B or vice versa. If I go with B on that leg, the longer one, angle B is over here. We often don't name this angle, it's just 90 degrees. But we could if we really wanted to. Let's call this C with the understanding it's 90 degrees. And that would be lowercase c that goes here. After labeling the triangle, Pythagorean's theorem says this. The side length C can be solved for in this particular way by first squaring and saying c squared is equal to a squared plus b squared. But you know, if you're looking at this part, that's the tie-in. C squared equals a squared plus b squared. Law of cosine says if this angle is just a little bit off, or maybe a really, really off, maybe it's 12 degrees, but even if it's, say, 88 degrees, just barely off of 90, there's a little bit more to the story, and you complete Pythagorean's theorem extension by putting in this piece right here. But even in ordinary Pythagorean's theorem, you can say this is minus 2 times A times B times cosine 90 degrees. And the reason that works is cosine 90 degrees is 0. This part just would cancel and become a 0 in that one case. If it's not 90 degrees, this term doesn't go away, and that's the extension. This is the full law of cosines that even works back in the right triangle over here. So that's the tie-in, kind of similar to what we were dealing with in section 8.1 with the area formula. But now here's what law of cosine says. Law of cosine states that the square of any side of a triangle, that's what we did here, c squared, is equal to the sum of the squares of the other two sides. Here's the sum of the squares of the other two sides, a squared plus b squared. And here's where it got interesting. minus twice the product of the other two sides and the cosine of the included angle. That's just another way to say minus 2 times AB cosine of the included angle is the angle between both A and B, the 90 degrees. But let's draw out our own new figure because we're usually using law of cosines without a right triangle. So let's make that angle C look a little bit different, maybe something like this. Extend it maybe a little bit further. So it doesn't look like there's any 90-degree triangle inside there whatsoever. Here's angle C, side length lowercase c. Here's where angle B goes, lowercase b, and likewise angle A and lowercase a. So with this new triangle here, no longer a right triangle, we have 3 different measurements. You can solve for the side length C. C squared would be just taking this angle C. You deal with the other two sides, A and B, square them, minus 2 times AB, and then take cosine of this side length C here. I notice this is alpha, beta, gamma. Let's use alpha, beta, gamma just to keep it as similar as possible. So this is alpha, beta, gamma. Sorry for that distraction there. We might as well keep the same angle measurements as they're using in the formula down below. On the second equation over here, it says if you're dealing with this side, if you want to solve for side length B, you would take B squared. A cosine of beta occurs, and you're using the included sides, A and C, angle beta in the middle. So these two would go together. And notice that's where your A squared, C squared comes in play, and then minus 2AC cosine beta. And whether we're calling them alphas, betas, or maybe something else entirely, maybe just an X, it's all about the relationship. Taking an angle and the opposite end, much like law of sines, but now it's just a different equation. Really just an extension of Pythagorean's theorem is a great way to think about it. And just to complete the color coding, if you're dealing with side A, if you wanted to solve for side length A, you would go to the opposite end, alpha, take the square of the included sides, C and B, square them, then minus 2 times the product of them, times cosine alpha. So putting them all 3 together, that's what law of cosines is saying. So the next problem is solving another triangle. We'll do a couple problems like those and then another application problem, just like at the close of the last set of notes. And this is our new tool that we're going to work with. Any questions whatsoever, folks, with just the statement of law of cosines? Okay, let's see if we can try it out in a brand new fresh problem then. It says solve the triangle for the unknown signs, round to the nearest 10th. I'm not really giving us a lot on this, but here's the tool that we're using, law of cosines. Can come to the rescue on this potentially. First thing to do, however, if you see this problem as, say, a homework problem, maybe a final exam question, is definitely draw out the triangle. Even if all you did was draw out the triangle and maybe you didn't get too far on this problem, maybe you ran out of time, I would consider anything you put down on paper on this as partial credit. So let's just get started. Side length A is 32.8 inches. So here's the 32.8 inches. These angles are pretty small, so that means the angle A that's over here is probably quite large. So let's see if I can make that look pretty large. Let me see if I can slightly make it look even larger. That looks like a rectangle. Hang on. It doesn't have to be a perfectly proportionate, believable diagram when you go to draw it out, but you know, sometimes it helps the mind to make it seem believable. And I'm trying to draw an angle that looks really large. Let's actually just write out what alpha is. I believe it's close to 120 degrees. It's 180 minus the 17.1 degrees from here, minus the 43.9 degrees from here. So the angle alpha is going to inform us on just what our diagram should look like. Take 180 minus 17.1 minus 43.9, and it's 119 degrees. So 119 degrees will look maybe about like that to my eye. Not quite perfect, but it's definitely more than a 90 degrees there. Here's where alpha is, 119 degrees. Now the side length that I was trying to draw in, 32.8 inches, seems like it could go in right here a little bit more reasonably. Let me see if I can get that back up. 32.8 inches equals A in this problem. All we have remaining is just angle measurements. One of them's 45 degrees almost, so it doesn't fit my diagram perfectly, but let's keep it just the way it is, just to convey your diagram doesn't have to be perfect. It's mainly just to organize the information. So I'll say gamma goes here, 17.1 degrees. Beta goes here, 43.9 degrees. And there's our setup so far. Let me drop those units just so it can make A more apparent. And when we look at this so far, one thing to note is law of cosines is pretty particular in how it works. You have to have two particular knowns. You have to know the angle alpha, and you have to know both the side length B, side length C, if you're trying to solve for A. If we're trying to solve for something else, say B in this problem, here's where B would be, here's where C would be. To solve for the side length B, we'd have to know the angle 43.9 degrees, which we do, so that's good. But you have to also know both A and C in this problem, but C is unknown, so we can't go that route by solving for angle B. If we work with angle C, or excuse me, side length C, you have to know the angle gamma. That's good because it's a known right there. But then you have to know both A and you have to know both B. A is known, but B is an unknown. So this is a pretty weird triangle. This triangle is kind of a reminder that as powerful a tool of law of cosines is, sometimes you can't even use it in the very first step. Even in this section called law of cosines, it kind of seems unfair in a way. So this is an important takeaway about this problem so far. Let me finish the rest of the color coding. Sometimes we have to do the following. We must start with law of sines, even to begin this one. Once we get, say, a side length B, we could use law of cosines on the side length C, and that's how we'll start off this one. So begin with law of sines. Let's solve for the side length B right here. So B divided by sine beta is going to be equal to, so if we're using this to this, we have one unknown B. And now if we say go from A to alpha, those are two knowns, so law of sines would work. So this would be A divided by sine alpha. If we plug in this information, this is just a quick right arrow, so we can save on vertical space. Plugging in the information gives us B equals sine, B divided by rather, sine 43.9 is equal to 32.8 for A divided by sine 119 in degrees. And that gives us the measurement B. B is finally equal to 32.8 times sine 43.9 degrees. Let me fix that penmanship there. Divide by sine 119 degrees. And finally, through law of sines, we can get our side length B out. So let's jam this one into the calculator. B is 32.8 sine 43.9 divided by sine 119 degrees. We're rounding to the nearest tenth, so this is 26.0, and this is inches. So 26.0 inches fills in there. Now, finally, with that information filled in, we can use law of cosines. Let's use law of cosines just to practice it as a technique to solve for the side length C. But you know, if you decide to use law of sines again to solve for the side length C, it would work. It makes law of cosines feel kind of useless in a way, but I assure you it's useful. It's the only thing that works on this one. You can't use law of sines on the very next example we'll take a look at. So just for the sake of practicing law of cosines, let's finish out this one by actually using it. So now here's law of cosines. I'm using this equation over here where the red dot is. Let me just kind of circle it to emphasize. It says the unknown side length we want to solve for can be solved by first squaring it. C squared would be equal to then these opposite legs, B squared plus C squared minus 2 times B times C times cosine of the angle included between B and C, which is the 17.1 degrees. So matching up that color coding, we're just using this directly. Here's law of cosines, and now we substitute in the information we have. Here's the nice thing about the law of cosines. Really, you could take a square root on this step if you wanted to, but I'll leave it just in this format. Everything here is just a big calculator operation. B squared is just 26.0 squared. C squared is just a, excuse me, that wasn't a C squared. That was supposed to be an A right there. Let me fix that. So that should have been an A in that spot. So A squared here and an A there. It looks like I missed a chat. Yeah, thanks for spotting that again, David. I missed your chat right when I was noticing it. It looks like it as well. It should have been an A squared and a B squared. I went B and A on that, so I got it backwards there. Thanks for spotting those. I appreciate your careful eye on this. So my A squared value, rather, is the 32.8 going inside here. Squared minus 2 times the side length B, which is 26.0. Multiplying the side length A, let me keep that in purple to emphasize that. Actually, we switched that to green. 32.8. Finally, multiply by cosine, 17.1 degrees. So all of that goes into the calculator, but at least you're not solving an equation really. You're just taking a square root at the end. So plugging that back into the calculator, the right-hand side here is 26 squared plus 32.8 squared minus 2 times 26.0 times 32.8 times cosine, 17.1 degrees. So that gives us 121.6394. C squared is 121.6394. But the next thing we immediately do is take the square root of both sides. Often there's a positive or minus here, we've mentioned before, but C has to be a positive length. So we just immediately take the positive root. So now finally, we can say square root of 121.6394. A few extra decimal places just for the sake of accuracy. And rounding this to one decimal place, it'll come out as 11.0 inches. So we've got it, folks. We have the unknown sides. C comes out as 11.0 inches. The other unknown side was B, came out as 26 inches. And we could have used law of sines again on this one, like we mentioned. But for the sake of practice, looks like it's good practice. Got to get those angles in exactly. This is what the law of cosines approach would look here. When we come back on Wednesday, we'll do law of cosines on this, the only way to start off this problem right here. But any last questions or comments, folks, on getting through this one? Okay, well, have a great night, folks. And thanks again for the careful eye on those weird mistakes I was plugging in on the notes on this set. we'll come back and finish off this law of cosine section next time, and looks like we'll start the polar coordinate section as well before going on the break. But have a great night, folks. I'll see you all on Wednesday.